So today I'll give a presentation about PCA. Then actually I'll focus on the mathematic theory behind the PCA. Then because there is a notebook of the book we use in MLT reading session, so therefore I mean like in their notebook there's implementation. So therefore this presentation I'll focus on really basic mathematic theory behind the PCA. Yeah. Then, first of all, I'll explain the basics of the PCA. Then after that, I'll explain probabilistic PCA. Yeah. So let's get started with basics of PCA. Yeah. So today, so we're gonna think about okay. Before that, so I'll explain about the PCA a little bit. So the PCA is basically the linear mapping or linear transformation from the original space to the subspace while keeping the information as much as possible. That's our main idea of PCA. Then, like in our PCA context, the information is equivalent to variance. So that's why, like, so I want to do the linear transformation, which retain the variance as much as possible. So then, okay, then let's say there is an observation. So that's our x from x1 to xn. Then for the simplicity, I'll talk about the linear transformation with the vector t. So vector t. Then the linear transformation is going to be like that. So t is a vector, so therefore the inner product of the transpose t and xn is going to be the transformation to z. That's our the transformation we're going to think here. So and also let's say the magnitude of the t will be 1. Yeah. So okay, then from this situation, we're gonna think about the PCA. So first of all, I'll review the really basic of the statistic. First of all, the sample mean of xn. So maybe so you may know. So the x bar is the 1 over n multiplied by the summation of the observation. So that's a sample meaning of xn. Then next, what is a covariance matrix? And matrix of x. So yeah, maybe you know the covariance matrix of x is like that. Yeah. This is a review of the really basics of the statistics. Then now, so as I have said, in the principal component analysis, so we want to perform the linear mapping while keeping the variance as much as possible. Therefore, we want to know the variance of the subspace means the variance of the z, right? So then, what is in order to compute the variance of z? So what is in order to compute the variance of Z, so the sample mean is required to compute that. So okay. Oh, it's really big. Mean of Z, yeah. Let's say Z bar. Of course, it's gonna be like that. Then from the definition, so from this definition, transpose. Oh, yeah, transpose. Xen, yeah. Then therefore, it's gonna be X bar because disparate. I don't know. Disparate. Oops. Disparate. Is the X bar, right? So yeah, that's why the mean of Z is the transpose T, the inner product of transpose T and X bar. Yeah. So then what we want to know is the variance of Z. Yeah. Yeah. Then from the definition, so we can compute the variance of Z. Oops. Yep. Okay. Yeah. Then so we can compute. Yeah, it's kind of the review of the statistics, right? Basics of the statistics. Maybe you can compute, together. Oh. Yeah, then so actually yeah. So then now disparate is the covariance matrix of X is the same, right? So let's say, let's say covariance of X is S, then S. That's why the variance of Z can be expressed like this. Yeah. So yeah. Then now so as I have said in a principal component analysis, so we want to lose any information while we perform the linear mapping. So therefore so I'd like to maximize this variance so as much as possible. Yeah, that's the idea of the principal component analysis. That's why. So now maximize the TS. Yep. Then also like I put a constraint. The magnitude of T is 1. Yep. Yeah, that's why. So it can be said a constraint optimization. Optimization. Yeah, because like this is a constraint. Then you know, the variance of Z should be maximized here. So then in our constraint optimization, one of the so kind of like tool to tackle this optimization, we can apply Lagrange multiplier. Lagrange, oh, I don't know the pronunciation, but Lagrange, I'm not sure. Anyway, so okay, Lagrange. Okay, thank you. Yeah. Then actually, yeah. So today, so I'm not gonna dig into like Lagrange multiplier here. So then, as a result, so we can get like that. So then, if you're familiar with the linear algebra, so you can say the T is the so from this equation, T is the eigenvector of the covariance matrix. I mean, like S, right? So yeah, that's why like the one of the like really important result from principal component analysis is that the vector which is used for linear mapping, then like the vector which maximizes the variance of the Z, I mean like the in subspace, is the eigenvector of the covariance matrix. That's a very important result of the principal component analysis. Yeah. Yeah, that's a kind of like take home message. Yeah. Anyway, so yeah, the T which maximizes the variance of Z is eigenvector of covariance matrix of X. Yeah. Then this vector is sometimes called the principal component. Yeah. Yep. And so if you multiply transpose D from left side to this equation, So then because like lambda is just like scalar, and that's why like, so yeah, I can write this way. Then as I have said, this is 1, right? So therefore, so as I have said, so this is a variance of the Z, right? So we computed here. Oh yeah, this one. Yeah. Therefore, so variance of the Z is the eigenvalue. This is the variance of Z. So yeah. that's a second like important result from principal component analysis. I mean, not only that the vector which maximizes the variance of Z is the eigenvector of covariance matrix of X, but also the variance of the principal component, variance on the principal component is eigenvalue. So that's a important result from the principal component analysis. So okay, I'll explain in with graph. For instance, okay, it's a little small. Okay, for instance, if there's a data like that. Okay, well, my handwriting is not good. Anyway, so then so first of all, like you can calculate the covariance matrix of this data. You know, first of all, you can compute the covariance matrix of observation. Yeah, then subsequently you can compute the eigenvector, which is equivalent to principal component. So vector, or the vector which is utilized for the linear mapping vector. So then, for instance, let's say, okay, this is a eigenvector. In the case, this direction is the principal component, right? Therefore, these data are linear transformed on this direction. Like this point is going to be like so each data point will be projected on this principal component. Like, then that's why the new data point is going to be here, 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 like that. So that's why we like transform the data from 2-dimension to the 1-dimension. Yeah, like that. Then, so as I have said, so, the variance of this data. So on the like principal component, the variance of the principal component is eigenvalue. Yeah. Yep. So yeah, so that's how it works. That's our principal component analysis. Yep. Yeah, hopefully it can help you understand the basics of the principal component analysis. Yeah. So it's a little weird to like talk on the Zoom for 20 minutes or 30 minutes. So. Yeah.
Sorry for not having
no,
more
no, no, no.
comments.
You have to sorry, but yeah, it's a little weird because like it's really, you know, yeah, really silent.
I understand.
From my side.
Yeah.
We are listening. Yeah, we are listening.
Okay. At least
But
you're
it's-
listening. Okay.
Yeah, it's going really well. Really well.
Oh, really?
Yeah.
Thank you. Yeah, I'm relieved to hear that. So, okay. Then that's our the basics of the principal component analysis. Then next so I introduced the probabilistic PCA. Probabilistic PCA. Yeah. Yeah. So yeah, then yeah. So literally, probabilistic PCA is a probabilistic approach for PCA. Then yeah, sometimes like someone asks why like then like so you apply probabilistic approach PCA, then yeah, there are like some benefit of using probabilistic approach for PCA. For instance, because this is a probabilistic approach, that's why you can kind of like deal with missing value of the observation in observation, so really naturally. So yeah, or because if you apply like Bayesian treatment for the PCA, then so, yeah, you can kind of like you can find I mean like the dimensionality of the principal subspace can be found like automatically. I mean using marginal likelihood or BIC or Bayesian factor. Yeah, yeah. So there are several benefits of applying probabilistic approach for PCA. Yeah, that's why. Yeah, so that's why I'll introduce the PCA. So yeah, I'll introduce the really basics of the PCA. So yeah. So in the probabilistic approach, we think about the generative process of the sample. Yeah, that's why. So let's say Z is a latent variable. Then Z follows the standard normal distribution. So do you know this notation? There's a normal distribution. Then I mean.
Yes, I think we had that in the book.
Oh,
so
okay.
The mean is 0, and the covariance matrix is an identity matrix.
Yeah. Okay. Oh, okay. Oh, in that case, okay, perfect. Then okay, let's say the probability density function of Z is a standard normal distribution, and we can define the conditional distribution of X given Z. So X is also like a probability variable. Oh, okay. Z and X is a probability variable, but like X is supposed to be observed, but Z will never, no, never. So I shouldn't say never, but Z is not observed. That's why like Z is called a latent variable. Yeah. So then probability density function of X given Z is the rose mu so squared. So I mean, like as I have said, so we can think about the generative process of the X observation. Then after we sample Z, I mean given Z, then like Z is transformed with like W. That's a as you mentioned, that's a linear transformation, and plus mu. That's a mean of the conditional distribution of X given Z. Then the covariance metric X will be isotropical. Tropical matrix. Yeah, isotropical means it's the scalar multiplication of the identity matrix. I mean, the diagonal component will be sigma squared. Then, other than that, that's a 0. That's isotropic. So, yeah, sometimes we call it, I think. Yep. Yeah. Then now we assume Z is M dimension. Then X is D dimension. Yeah. Oh, no. D dimension also. What is this? D dimension. Then we assume, so I assume D is greater than M. Actually, technically, the M doesn't has to be less than D. But however, for the simplicity of the explanation, so we assume D is greater than M here. So yeah. Then, so now we have the distribution of Z and the conditional distribution of X given Z. So now we will know marginal, marginal distribution of X. Yeah. I don't know the marginal distribution was written on the book or not, but yeah. So actually, the marginal distribution of X can be obtained by integrating out Z from the joint distribution of X and Z. Yeah. So I mean. Yep. These are from the here. So then yeah. So I can calculate this this marginal distribution step by step, but I think the time is limited. That's why okay. I'm gonna write the result here. Yep. These are marginal distribution. That's a kind of like yeah, structure, not structure, but yeah, idea of the probabilistic PCA. Then in a like probabilistic approach, I think that the understanding for the generative process is really, really important. So therefore, as a last of my presentation, I will explain the generative process in a really simple way. So let's say example is X is 2 dimension. And then Z is 1 dimension, right? Yep. Then, as I have said, the Z is sampled from standard normal distribution, right? But therefore, sample Z. Yep. I wish I could write normal distribution more like precisely.
No one can draw the normal distribution. It's terrible.
Okay, thank you.
Hard for me very also, so don't worry about it. But this is excellent.
Okay, that's flatter. Yeah, I flatter. So. Okay, so yeah, let's say this is a standard distribution. Then so we sample from this distribution. Okay, let's say here or here or here. Yeah. Anyway, then second of all, so then I introduced the conditional distribution of x, right? Yeah. Okay, I will write it down here. The probability of x given z is no. The transformation is w in mu, and yeah. So then let's say w is here, w, yeah. Then so wz means in this example the scale, that's a constant multiplier of w, right? Z is a one dimension, so therefore let's say okay, this is a wz. It's depend on the sample from here. So here or here. Okay. Then let's say wz is this. Then mu. Okay. This is mu. Then it means the plus wz plus mu. Maybe you may know the addition of the vector, right? Yeah. That's why wz plus mu means here. Then this is, so mean is here, right? I mean, then there's an isotropical covariance matrix. That's why the contour of the normal distribution will be like that. Then so we sample, for example, here or something like that, right? Yeah, that's how it's sample. Oh, okay, sample x. Yeah, from conditional distribution. Yeah. Then so maybe you notice that z is sample from here or here. So, but like that, I mean here is this. The mean is 0. Therefore, the z will be I mean wz plus mu will be like if the z is minus, like here, then wz is mu is a little this side, right? Then if the plus is sampled in here, but the center over here, so that's why sampling will be performed along this direction. If there is a plus mu is here, then sample from this normal distribution. Then if there is a plus mu is here, then sample from here. If here is a little, a little outlier, I'm not sure, but from normal distribution, and then yeah, that's how it works. Then as a marginal distribution, yeah. distribution said the sampling is performed along this line. Therefore, the marginal distribution, the normal distribution, it's better to write here. Marginal likelihood, okay. Mu WT plus sigma square. Yeah. Then the marginal distribution will be like that. This is a contour of the normal distribution. Yeah. So that's easy. These are the generative process of the probabilistic of the PCA. Yeah. Hopefully, it help you understand the probabilistic PCA. Yeah. So then, that's all my presentation. So let's say take-home message is the first of all, from basics of the principal component analysis is first of all, the vector which maximizes the variance of the like subspace is the eigenvector of the covariance matrix of X. So, okay. I should. It's a very important thing, and also the variance of the principal component is the eigenvalue. Yeah. Then also the sampling process I explained here, is also really important because in a probabilistic approach, the understanding the sampling process is really like imperative, to understand well. Yeah. So that's all. That's my presentation. Thank you for listening.
Thank you for giving the presentation.
Yeah, excellent. Thank you so much. I think we have another 10-15 minutes for questions if you guys have any questions.
I actually have one question. And let me use the function of Zoom to also write here. So this is what you get for can you see my, okay. So this is what the end result sort of probabilistic PCA, right?
Mm-hmm. Yep.
And if I understand this correctly, this basically what it does. The regular PCA would compress the 2D data into points along this line, right?
Wow, you can write on my.
Yes, but it's not your program. It's on your screen.
Oh,
so
I see.
Notation, so it's
I
a little
didn't
bit
know
different.
That.
So
but it's really usable.
This is Zoom magic.
Oh, Zoom magic. Okay, thank you.
I mean, not Zoom magic. That's not the name. I'm just calling it like that. So the simple PCA, it sort of makes it possible to take just this one line and encode the 2D data as one component data, right?
Yep.
And then have all these points on this exact line. And the extra, what we get from probabilistic PCA is that actually and this is what I want to verify if I understand this correctly. So if I make a cut of this like here, and then based on so basically I get a probability distribution that, okay, if my data point is compressed to be here, then I have a certain probability that, I have a probability distribution along this line where it could be, or well, actually, no, sorry. Okay, I think I got it. So okay, wait, let me delete this. And I think this was what I explained now, it was wrong. And I think I have a better explanation. So when I get a data point that my compressed component is here, then it actually means that I get instead of getting just one point, I get a full probability distribution, which is drawn as this contour plot of probabilities, right?
Mm-hmm.
Okay, well, basically that was my question. Sorry, I just needed to double check. So instead of having like one precise point, now I get these a distribution, which is in this picture represented by the contour plot.
Yeah, so I'm not sure whether I understand your point or not, but yeah, this contour means how the observation is sampled. So
maybe I can reformulate the question. So
okay.
how is probabilistic? I mean, I understand how the simple PCA is used. It's like compression. So try to encode the most of the original data using less space, and we are using the principal components, and which kind of describe most of the whole data set. And how is the probabilistic version used?
That's really interesting question. So you said in a probabilistic PCA, how the data point is going to be compressed to for instance, one dimension. That's correct?
Yes, and then decompressed also. So how is it? What's your like main use case for probabilistic PCA?
So in the case like okay. For instance, like I have said, the probability of Z is right. Then Bx Bx Z is Z plus mu. Then so
wait a little bit, because you have considerable delay between the screen share and the oh yeah, okay, now it arrived.
Okay. It's really funny. So there is a okay, you removed. Okay. So then from the observation, you want to know what looks like on the subspace. So that's how like we can think. So in the case like from this distribution and observation x1 to xn, then we can calculate the posterior distribution of the Z given X. Yeah, that's a
yes.
Yep. So okay, it's equivalent PZ ZN oops, nope, and the X side and yeah. Then you can compute. Then so yeah. Then I mean you can compute the posterior distribution, which is called posterior distribution.
Yes.
Yeah. Then that's why like actually in a probabilistic approach or a specific technically in a Bayesian approach. It's not point estimation. We always put the distribution.
Yeah.
So what we want to know. So that's why now we want to know the subspace, right? So what looks like in subspace? In the case like it's in a Bayesian setting or probabilistic setting, it's equivalent to computing the posterior distribution of Z. That's why, for instance, like there is a data x1, right? Observation.
And the posterior distribution is the one that you get with the contour plot on the 3 figures you drew.
No. Actually, this contour plot is the marginal distribution.
Oh, okay.
Yeah, this is actually technically just a PX. Yes. Yeah. The is the
that's
like
the kind of like the how should I say? It's not the reconstruction, but the probability distribution, where it should be reconstructed. No.
I mean, that's a. How can I?
I'm not sure if that makes sense. I'm not. Probability is not my strong side.
Okay. So if you know the natural probability distribution, like it's really difficult, but that's a distribution of x, which is like integrate out z. So that's a like purely marginal distribution. However, like what I said was the posterior distribution of z given x. That's why like this contour is not about the posterior distribution. So that's why you can find the distribution of kind of like distribution. We can find the distribution of z.
So basically, your goal is to get the distribution of z, right?
Yep. Yeah. That's true.
And z is the distribution of the vector representing the compressed data point. So
Yeah.
I'm trying to make my connections with the simple PCA. I'm probably oversimplifying stuff, but so like what you have in the regular PCA, z would be your compressed data point after the PCA. And now instead of getting one concrete data point, one concrete compressed point, you have a distribution of a point.
So okay. How can I explain? So in a basic PCA, so the data is like project to the principal component, right?
Yes.
And in a probabilistic setting, so we think about the data is from like samples from latent space. That's why like this is kind of like
instead of saying
latent space, then to the actual like observation, the space where the x is sampled, then so from that we can compute the posterior distribution. Then as a result, we have the distribution like it's really bad handwriting. So anyway, so this is I don't know 2.5 or something. So anyway, so that's why like that's another point estimation, but those are like so you can get the distribution of z,
where it is, and also the probability, how certain you are where it is, right?
Yeah, that's true. So this is the same like in our basic PCA. So you can after projected, you can say so this is the inner one dimension. This is a 2.5 or something, right? So this is right. So but here we have the distribution.
Yes.
Yeah. That's how it works in our.
Can I add? So that is
please.
So that is why you're drawing the contour. The contour actually are the contours of a Gaussian, right?
Yes. You mean contour of?
I like these circles here. We can no. The third one.
Oh, this one.
This contour.
Yes. The contours here is like you can imagine a Gaussian popping out the screen, right? And those are
that's true. So because like we assume there's a linear relation between the subspace of their observation. That's why also like this looks like you can say, oh, this looks like the observation is sampled from the Gaussian distribution, right?
Wait. No,
Yeah.
there's but that is for 1 point. The contour is for 1 point.
Yep.
Right. But the other one is not. So that means we have many of these contours, right? If we are going to relate this picture number 3 with the classical PCA, which is the first one you draw, which has a variance, right?
Yeah.
I see. So it's basically like a generalization of not discrete, but what is the reverse of probabilistic?
Deterministic.
Deterministic, yeah. Yes. So if you can you go back to your previous slide? Sorry, the classical PCA. Yes. So yes, no, the one with the variance. Yes, thank you. Yeah. So here we are sure that the points are mapped to that line, right? So it's deterministic, but probabilistic PCA says it probably is around somewhere here. Is that correct understanding?
Yes, that's correct. Yeah, because like the posterior distribution capture the uncertainty.
Okay,
Right.
thank you.
Yeah.